Hello, everyone. Thank you so much for coming. We are very happy to have with us Professor Miroslav Staron from the University of Gothenburg and Chalmers in Gothenburg, Sweden. He's going to talk to us today about his work on autonomous AI-based measurement systems in Ericsson, Volvo, and a bunch of other companies. So without much further ado.
All right, great, thanks. First of all, thanks for having me. I really appreciate coming over to Microsoft Research. So who am I? I'm, as Nachi said, professor in software engineering. I work mostly with software measurement in different areas and mostly working with companies like Ericsson and Volvo on that. I'm also active in standardization committees, most recently in the 25,000 standards and the revision of those. And those are basically the pictures of things that we are doing together with in this case, Ericsson and Volvo. So different kind of dashboards and measurement system for decision support. And I brought the book that we wrote together with Wilhelm, my colleague. You can browse it, and I will leave the copy with Nachi. Yeah, so this is basically our team. It's both for from academia and industry. And both me and Wilhelm have been working together for the past 12, 13 years now on measurement systems. We actually both, we located about 200 meters away from each other to different places, so we work a lot on software measurement. And the context of the whole collaboration is the Software Center, which is 11 companies and 5 universities. And it's a collaboration that is quite similar to what you have at Microsoft Research, but a bit different, of course. It's more companies, it's more universities. And it's focused on things like continuous delivery, on architecting, on measurement and management, and customer data and ecosystems, working with companies like Volvo or Grundfos that are makers of pumps, Jeppesen, who is working with maps, Bosch and Siemens, you know, of course. Not. So, why we're so excited about working with the Software Center is because it gives us an opportunity to work in a very different way than most academic research is done. So, since this is a formalized agreement, we have the possibility to go to one company, test the idea, and after a while go to another company, test the idea and improve that further, and then move on to more and more companies. So this is how we basically do. We take, for instance, the code churning that Nachi and some of your colleagues have written a while back, and then we apply that at Ericsson. And then a colleague of mine, Robert, has introduced me to heat maps. So we used heat maps to visualize churning in the large product base. And after a while, we took that idea from Ericsson to SAP, where they basically said that, well, if you can visualize that, maybe you can also predict the coming changes or predict changes that should be done but were not done. So we did this that we called change waves. And based on that, when we took it to Volvo Trucks, we could also predict the impact of change waves and code churning on the quality, both of the quality of the code, but also quality of the final truck that is driving around. And then in the end, we took it to Volvo Cars, where we could actually bring in both defects and requirements and code into one dashboard that could predict the wave of changes in the requirements that would spread to the source code, that would spread to the test cases, that would spread to the quality. So we could basically predict the things about half a year in advance on it. That this kind of work resulted in roughly 40,000 measurement systems that we built at different companies. And I will introduce you to what a measurement system is later on. But you could see this, for example, as a type of you could see this as a gadget, which visualizes some sort of measurements that are being processed in completely autonomous way based on either big databases, Excel or BI behind it. That has mechanism of, for example, self-healing, so that those 40,000 measurement systems, if they crash, they could actually repair themselves. So this infrastructure of 40,000 people is maintained by roughly 2.5 person per year, which is very little given the amount of work that they do. So instead of, thanks to the self-healing that we did, was that instead of spending hours a week, they could spend hours a month on maintaining those things and then focus on new development. We have worked a lot with things about information quality. So if you see a number at the very top, the defect backlog 8, and you see the red dot, that red dot is actually showing if you can trust the number or not. So even though you can mathematically get a number of defects, there could be a lot of properties. For instance, the database may not have been updated. The defects are outside of the limits. So even if you see 8, maybe you could expect 20. So where are the other missing defects and so on? So we build a lot of checks into the data that gives the stakeholder some understanding if he or she could trust that information on it. And then we, of course, have estimations of things. For instance, we applied those change waves analysis at Volvo. So we could predict if a change in the standard of AutoSAR, how much that would cost to implement in a new Volvo car. And that analysis was usually done during a few months, but thanks to Darko and his work, they could do it in days. They could press a button, get a lot of information, build a model, and then they could just evaluate if that model was correct or not. And then, of course, what we also did is we could also apply exactly the same things to look at the quality of requirements. So we could pinpoint requirements that did not fulfill specific criteria very early during the review. So if you could review a specification with 100,000 requirements, instead of spending weeks of reading all of them and trying to build a mental model, that tool would allow you to focus on, say, 200 requirements that really need your attention. Maybe they are not consistent, or they are not coherent, or they need some extra information, or maybe they're just wrong, plain in usage. So that is what we did quite manually. Now what we're doing right now is focusing a lot of applying this machine learning techniques and artificial intelligence on measurement. So quite normally when you have a measurement program in a company, you take a lot of data and try to build up some decision support. You could see this as a BI, for instance, right? It's an example of it. But that requires a lot of manual effort to find out what the questions are, what does the stakeholder want, who is the stakeholder, what their goals are, and what kind of measurements you do. But if we apply, for example, machine learning or AI, those systems could basically tell you what is it that you need to focus on. So in a case of a company who has 40,000 measurement systems and maybe hundreds of thousands of measurements, the AI could pick out those measurements that are off limits today and focus your attention. So if you, for instance, focus too much on quality and then forget that the important part is to ship the features in your product, the measurement system will start flagging that you're lagging behind in the feature development. Or vice versa. If you just focus on new development but don't test enough, this AI will tell you that now you should really focus on testing because your test progress is slowing down. And because of that, you suffer from quality and so on. It could also give you a lot of simulations on that. Where we came from is that we started with working on manual predictions a long time ago. We built a lot of prediction models together with Ericsson. And then we found out that those predictions are very good, but they are very unreliable in many cases because they are very product specific. It's very difficult to build a uniform model that will predict number of defects in any product in the world. So what we came up with was that we could automate certain quality checks. Look, for example, of if the variables or metrics are outside of limits. And if they are outside of limits, we could tell you that, okay, this is the model that you can use. You will get a number, but you shouldn't trust the number because the values are outside of the range that are usually predicted for that. And that we focus on mostly things like defect and faults, failures in the product. And then we said that that's, of course, a very good thing, but it's a very reactive thing. So we moved on to code stability visualization, where we used code churning and basically characteristics of code churning to make prediction models. And then we could build up things like robust measurement programs based on that. So be able to predict and warn stakeholders a few months before something happened that you're going to have problems with this product, or you're going to have problems with this module, or you're going to have problems with that type of customers. And then what we do today is we do this AI-based software analytics when we build in a lot of intelligence in the measurement code base. So instead of spending years and months to analyze your data, the AI gives you the answers directly by itself, so to say. And that brings me to how do we do that, right? So we if you take companies like Ericsson or Volvo, or any other company that work, they have something they call measurement program, right? So they have stakeholders, they have information needs, they measure things, they measure product, they measure processes, productivity, quality, and aspects like that, and they try to put them as key performance indicators to put on big monitors and show, how good are we today? I mean, how many customers did we get? How many customers do we lose? But those are very reactive. They are set up by people who have domain knowledge, and these people based all of that on their experience. But as you know, the world is not built on experience. The world is changing all the time. So if you build things based on your experience, quite often you can miss something. So what we do is we provide more decision support to exchange experience with some new ideas. So we build, for example, algorithms based on decision trees to come up with new metrics that will tell you that this is an aspect that you don't really cover based on applied statistics and things like that. And we do this quite often. We have a repository of over 2,000 different metrics that we constantly increase and show different aspects of what we do. We have this self-healing infrastructure that does it. I mean, imagine if you're processing this amount of data, you cannot really manually monitor that everything is right all the time. So what we have is this the systems that do a lot of magic behind the scenes, looking at, for instance, collinearity of data, so the mathematical properties of the data. It looks at the processes behind the data. For instance, have people been reporting defects into the system? Have test cases been executed? Have code been checked into the repositories? All kinds of things. And based on those aspects, we could tell that, for instance, something has happened in the data, that, for example, people have stopped checking in the code into Git repository, meaning that one has to look into that and decide if that's something that we should ignore or is that something that is not required. Yes?
So what does self-healing entail here? Like, what does that practically mean?
So in practice, that means that sometimes if you measure something, you get, say, the closest example, if someone doesn't report a defect, you may get a division by 0 somewhere, right? And in normal cases, you could visualize that either as a, infinity or error or 0. But that, even if that's a number, it doesn't mean that it's a correct number. So what the self-healing does is that it looks into why did we get a missing defect. And if that's, for example, a missing connection to a database, it will try to pull the database a few more times to try to get the data. And maybe the database needs to be restarted. So the self-healing mechanism knows that it's a database, it could be restarted that way, so it restarts the database. And does a lot of those kind of checks. And in most cases, it can fix the problem with the missing data in a much more meaningful way than just showing 0 on that.
The whole step, like hardware, operating system, applications, or just applications?
From your perspective, that would be mostly applications. We don't do operating system. We don't go that deep. All right? All right, let me move on then. And that is important with this because this is how a measurement system could be visualized, right? So it's everything from mobile phone apps, gadgets in all times, to websites, to built-in continuous integration, or things that are based on SonarQube or on Tableau dashboards or Power BI, all kinds of systems. But that's just the visualization, the final step, right? What we do with the AI or machine learning is that we change those visualizations automatically. So in the old days, one could see that this was if you take this picture, that was a measurement system showing bottlenecks in a software development program. So it was divided by phases, and one could look at different activities and the throughput and queues and flow in the system. But as you see, that's quite cluttered, right? It's many different diagrams and don't really know where to look for. So what we do today instead of that is we take away that picture and then let the machine learning look at decision trees and regression models to look at the dependencies between different metrics, and then based on the deviations from dependencies, we could basically say that, for instance, now you have a lot of Q in the defect handling, right? So we visualize only this part and say you should focus on that. But if you have little defects, but a lot of, for example, a lot of development, a lot of integration, we could visualize something that's not on this diagram, that is a testing, saying that, okay, you have developing a lot, things are happening, but we don't see any defects, meaning that there must be something wrong with your testing. So look at your testing. Are you testing enough? Are you testing the right thing? Are you maybe missing test cases? Where are the things that try to find out where are the things that are not really visualized, are not really there. Yes?
How did you go about training the models that direct people's attention?
So what we do is that at the beginning we train that on historical data, but then we have a model that over time looks at when we should stop using this particular trained model and should retrain the data. So we have an ensemble learner that over time changes. Trains the model. It's used on decision trees and the random forest. And over time, when we see that this model is getting a bit off charts, then we take away that and we train that on new model continuously, so to say.
But this was supervised learning, right? So where do the labels come from? Like who? I mean, at some point, you must have a label that says this metric is important at this moment.
So we have two things. One it comes from for example, information quality. When we notice that sometimes, for instance, this data is being off the chart, for example, that we expect the defects to be no more than, say, 10 per day, but now we just have 20 every week. So that lamp is going to go red a bit more and more, and then someone looks at that and say, okay, should we retrain the model, or should we go to the team and say, look, what's wrong with your testing? So that's one aspect. The other aspect is that if we get a new data type, for instance, or new metric, or you could call it a new feature for the model, then we try to retrain the model based on some simple algorithm, and then we use active learning when things are, for example, random forest give us a high probability that the algorithm doesn't know where to classify that aspect. Then the quality manager or team leader has to press the button. Is that okay or not okay? So for the beginning, we learn using basically active learning. So those two things, information quality and active learning. Okay. All right. Yeah, and if it comes to this information quality, we look at two things. One, so the one I talked about is the more internal quality, when we look at the kind of mathematical properties of the data, but we also look at the external quality. What does the stakeholder think about the data? So this situation when the metric is outside of the limits. And it's all based on the ISO 15939 standard, which is a standard showing how the information in a measurement system flows, basically, from the attributes or products until the information needs of the stakeholder, how that thing is built up. And this whole monitoring of information quality, now this is just a set of checks. This whole monitoring is based on checking properties of every step of that calculation. That's a basic idea. And then if something goes wrong, like this one, for instance, that this check says that the raw data was not updated. For example, someone did not report any defects yesterday. Then that will be more for a information system designer, but for the stakeholder, it will just show red without saying exactly what is the problem. Because the stakeholder, think about, for instance, product manager. The product manager doesn't know exactly which raw data is used and how that is used and so on. So he only gets the indication that for this moment, you cannot really trust that number. But the metric designer can go in. He also gets that number on his or her screen, and he can go in and check exactly which data was not updated and what to do about that. Right? And as I said, it's based on the ISO 15939 standard. And how we do machine learning in that is that we add a lot of things around that basic idea of checks, right? So if you have a lot of checks, you could use the checks as labels for training of machine learning to some extent. And we basically do this data collection So that was what you saw, it simplified on the right-hand side. And on the left-hand side are the things that are connected to the organization. For example, how do we know that a specific KPI is really important for that particular organization? How do we know that the company X has to focus on speed and not on quality? What does it say? And then we look at, for example, of reference models from other industries or other companies and try to compare them and see that company X is much slower than company B. And then company B is in the same area, but they could develop a lot faster or integrate a lot faster. And there comes the strength of the collaboration we have in the software center. We have different companies that are quite open to each other. So we could compare and they could learn from each other and they could say, look, in our model we could integrate within, say, half an hour, and you could integrate and you need a week to integrate your software. So there is a possibility for improvement on that. And thanks to those, all this work that we did based on code sharing from you, for instance, we could teach the models to find where the problems in the code could actually pop up based on the dependencies between the code churns and, for example, testing. So we have a model, a regression model that shows where are the missing test cases or which test cases we could suggest to execute based on a change in a specific code module. We also have this, we also work on the measurements and their quality from the perspective of the impact that they have on the company. So for example, we look at the entire measurement program, and an entire measurement program could have maybe up to 500 measurements in them or indicators. And we look and try to identify which of the indicators are the leading ones. So if you could only pick 10% of your indicators, so 50 indicators out of 500, which 50 would you pick? Which 50 are the most important ones? And you could look at, of course, at mathematical properties like collinearity and codependency and try to predict one another. But what you could lose is, of course, the slight deviations when for instance, you have two indicators and they are in 99% of the weeks they show the same status, but this 1% of the weeks when they actually show different status, and that's 1% when it's really important. So we do a lot of work with the stakeholders when they provide us with different weights of different measurements or measurement aspects in the measurement program. And based on those aspects, what we do is we could also build a model saying that even if mathematically two indicators are correlated, the important thing is to show when they deviate from one another, that sort of 1% when they are not, when the correlation is not perfect on that. And that, again, helps us a lot if we are if we're working with multiple companies, when we do a lot of work with different sectors, different types of stakeholders, and different type of metrics. And types of metrics, for example, this is our metric portfolio sort of summary, the areas which we use. For example, we have cloud computing measurements, things like anything from stability of a cloud environment to complexity of the code that is behind the cloud, execution, scalability, and so on. But also project metrics, for example, how fast we deploy new features on the customer site, how fast we test, how many reviews we do. We look at the product, we look at organizational performance. For instance, how fast can a feature go from an idea to actually implement it, feature and ship to a customer, which is important in areas like telecom or automotive today. We look at the customer side, for example, product delivery. How do we know that the customer is actually happy with the product delivery? And I know that you work with that a lot, but in the areas when, for example, automotive is not as easy because you ship the car and then it's out there driving, so you don't really collect the same kind of data. It's not a web system, not connected all the time. So it's difficult to find that kind of information. But then we have models and things that help us out with this. And if you're interested, I could show you more about those metrics. And they come mostly from either different papers or from the empirical evidence of the companies that we work with. So we look at what they are measuring today and what they know what works and what doesn't work. which could be quite a lot of good evidence. And instead of predicting, I mean, previously we have focused a lot on predicting the values of metric, for example, the defects. We wanted to predict when the defects would come and how many would come in a specific product, what we should do, where they would come, so the location of the defects. But right now, what we try to predict is we try to predict the sort of events rather than things related to defects. So the numbers are no longer important. What is important is the trend. Are we going to be better in a week or two, or are we going to be worse? Should we prepare for something, or we should not on it? Which sort of is the entry point, of course, to all of the mathematics behind this, but it's communicated in much easier way, so to say. So this is showing a gadget. It's roughly 10 years old. Yeah, roughly 10 years old. But today we use mobile phone apps and we use emails instead of gadgets. So the stakeholders don't have to look at anything at all. They will just get an email when something is out of range, or they can get an SMS or on a ping in a mobile phone on that, which is a tremendous difference, because then we could monitor more and more data, and for that we need this machine learning and algorithms to monitor, and then we only support the stakeholders when something is really required and really needed for that. And of course we use a lot of mathematics behind that, so very simple formulas that are not based on so this is an old formula showing how many weeks are needed to ship the software to a customer. So in that case, it's a work we did with Ericsson. So if a customer to Ericsson calls and say, I want to have the latest and greatest, they need to know how many weeks they need to actually provide them with the latest and greatest software on their side. And then they can also have this on a mobile phone app, how that works in this. And that was about 8 years ago when we started working with that. That was very good because it showed a very succinct and very compact way of showing the quality of the product and the plan of deployment of that. But that wasn't enough. What was required was to have a more prediction view of that. So what we did in one of the studies is that we actually used heat maps to look at the profile of a code. So we would like to know, where do people do changes in the code base and how do they do that? And you could see two patterns. In that example, this is an agile software development, where you see the intensity of the color basically says how much code was changed per a particular week, a particular module. And as you see in an agile development, you have changes all over the place on that. But this is an example of a product which is more a platform versus application based. And you see that quite a lot, that there is a group of people working with a platform, and they do a lot of work all the time, as in those cases. And then you see fragments of the code which are basically different applications. And there you see a completely different patterns. You see not red all over the place, but you see blobs when they focus on a specific feature that is, or a specific application in that area. And then they move on to another one, and so on and so on. And this way of visualizing was actually a big hit, showing that you could predict things, for example, missing updates. So if you look at the middle of that heat map, one can, of course, start asking the question, why don't we do anything in that area? What's the area for? And if historically you build a model saying that there are some changes in this area, and as you see that those dots are sometimes have this property that one happens before the other. So you could actually try to build a model, as I said, the code change wave, saying that if always this module is changed a week before that module, I mean, why don't we have that change in some week? So you could identify missing changes, for example, right? And they don't have to be missing changes, but it's definitely an input for someone to look at that code and say, look, if you have usually make change to module B after you make a change in module A, why haven't you done that this time? That kind of way of visualizing code also helps the teams to prioritize test cases. So they could look at this model and say, So, now in this particular week, we work very much in those two modules. Have we tested those modules at the same speed, or have we tested another part of code? How do we know that the code quality is so good on that? So input to the decision. And at the beginning, we had this as a manual input. Right now, we're building more of a prediction models that could tell that, for instance, if we have exactly the same heat map, but on the test cases, we could show that in the same week, we have usually made a change in module A, and then usually test case X have reacted on that, sort of found a defect. We could prioritize test cases based on code churning and try to provide this as a feedback to the test leader, saying, look, this is how your test strategy should be designed in the next few weeks, if your changes are going to be like that. And that kind of approach led us also to looking at the standards for the automotive. So Darko, who is working for Volvo, has been looking at changes in the AUTOSAR standard, which is a huge standard, kind of like an operating system for a car. You could see this that way. And what he could do with his change waves and with this optimization of the code, he could predict the impact of a particular change in the standard on the cost of a development of a car. So that standard could say that, for instance, we add one attribute to some construct or some function in this, say, operating system, and he could predict how much that will cost the company in terms of change management, in terms of new development. Is the new version of the operating system or standard going to be backward compatible with the software we have, and so on and so on. What he could also do is that he could look at the Pareto front and could identify the best combination of features. So if you develop a car and say, I want to have this particular feature, you could find that in this and say, okay, if I want to have this feature, all of these features I get for free because I still need to develop that because of that particular feature, right? So that gives you a discovery of new business possibilities when you develop those kind of big systems, right? And then we talk about, 100 to 200 different computers and tens of thousands of different functions in a car. So it gets pretty complex with that. And thanks to this analysis of the changes, he could basically quickly predict and provide more information to people on that. And based on that model, he could also say that if we want to implement, say, this feature, and what's the cost to implement the next one, and what is this difference? So what do we get if we move on to the next level, so to say, right? And identified also the sort of optimum when we no longer, where the cost is basically much more than the benefit that you get from those features that you ship to the customers, which is pretty interesting for car manufacturers. Vart, on the other hand, he looked at the very similar thing, but he looked at that from the perspective of requirements, right? So if you have a 100,000 requirements specification, you would like to quickly find out the requirements that are connected, that are incoherent, that are really badly written, to focus your effort on that. So he developed that model based on simple measurements of requirements, kind of like a very, very basic natural language processing, but without any semantics. And he could build that part of the tool chain at the company. So right now, when this company is working with requirements, when they specify the requirement, they get directly a very quick feedback saying how good or how bad that requirement is. And they also could get an impact of why this is a good or a bad requirement very quickly. I could give you an example of that is, for instance, if you are implementing something and then you say that in your new truck, you should implement standard 25026, which is a very nice requirement if you write it. But then you open up the standard 25026, that's like 2,000 pages. So what do you mean by implement the standard? What, in practice, which page? So this model would catch this situation and say, look, in this requirement, there's something fishy. It looks very nice, but it's very inspecific, right? You need to be very clear about which page or which area of the standard you should implement, so to say, which saves the companies hundreds of engineering hours in backtracking requirements that should be specified a bit better at the beginning of the development cycles. Something that my colleague Mirek is working on mostly is now looking at the code. So if you look at the professional companies that develop software like you have coding guidelines, what people can do and cannot do in the code. And you can use, of course, style checkers to check many of those, but many of the guidelines cannot really be done using style checkers, because writing the rule for that would be very, very difficult. It's not straightforward to do that. So what my colleague is doing is he's building a machine learning model to train how to recognize violations in the design by providing examples of a code. So when you do a review in Gerrit, you look at the code that's been reviewed and say, this is a good code, that is a bad code. And then this machine learning algorithm learns which is a good and bad code. So the next time you get a support in Gerrit saying, look, this is probably a rule violation in that code, or that code looks good to me. So over time, that review speed gets very much shortened, because you don't have to read the code anymore. The machine learning algorithm gives you a good example of what is a violation or not on it. And of course, since this is all based on probabilities, you never get 100% correctness, right? So if we look at how far we can go, for very big code bases, we need to train an algorithm with, say, roughly 300 lines of code, and then we get roughly 70% accuracy in recognizing, which for a company that does review on a daily basis is a lot of speed up, because they get 2 out of 3 lines that they identified is actually true positive, and 1 line is false positive. But that's okay, because they still can take this stand on their own. And the novelty of this is that what we do is we don't use any static models. We teach the machine learning based on the code. So we show them the algorithm, the code, and we tag the lines which are good and which are bad, and then it builds a model by itself, looking at things like which words are used, what kind of patterns are used in the code, and what kind of how long the lines are, how many brackets one uses in the line of code, and things like that. Yeah. And again, thanks to the collaboration with different companies in the software center, we could test exactly the same rules at different companies and look at how they think about coding violations. Because I know if you do code reviews, but if you've done code review, the rules look very simple on paper. But then if you look at the code and have to decide if a rule is violated or not, it's not always that straightforward, because sometimes there is still quite a lot of interpretation how the rule should be done. And thanks to this thanks to using machine learning and decision trees, one could actually backtrack how things are working and when things are going bad, so to say. You're awfully quiet. I mean, you don't have any questions, or you've already done that, right? Okay. So I'm preaching to the choir. What we did also is we studied the patterns of how measurement information is actually spread across the companies. So instead of having big monitors at landscapes that everyone looks at and no one really gets a lot of information from, we studied who is communicating with whom in a company, and then we could divert the information or direct the information directly to the people who are interested on that. So looking at could be through email communications, could be through the dashboards that automatically adapt where people sit. Different things, right? Yeah. And then we also look at things when people build dashboards. So think about, for example, if they have to decide between using a Power BI or a gadget or an email, how do they decide today? Well, today they basically look at what the purpose of that is and find out what they want to do. But we have this model that helps them to choose quite quickly. So it's like you can see like a slider when you configure buying a new car or buying a new mobile phone. We do exactly the same thing for a dashboard. So you do play around with different parameters, and then by the end of the day, you get an idea about what kind of dashboard you are building. And it could also help you, in some cases, to choose what kind of measurements one could use. Based on studying those patterns, we also found out that instead of working with measurements in terms of dashboards, quite many people actually want to work with measurements in terms of a cloud. So they would like to have their own private measurement system put into in our own cloud environment, which is extremely simple but still quite powerful, and then spread their information to other colleagues in a very simple way. That will be automatically updated and automatically spread out. We found out that it could reduce up to 50% of the cost of the measurement for the company. And then increase, of course, empowerment of the teams who want to have their own measurements instead of having a central body steering that. That is based, of course, on very simple technology. So it's not like Azure cloud. It's much, much simpler. It's maybe 1,000 lines of code of the cloud environment that we use. Sorry?
It's not a lot.
No, exactly. That's not a lot. That's an extremely simple cloud, right? But it's extremely powerful for that particular purpose, right? Because what it basically does, it spreads around different messages to different agents and then tells them to update measurement systems, right? So it's extremely simple, but extremely powerful. And things that we have discovered thanks to that kind of environment was that it's much more robust to changes in the environment. So, for example, if one computer goes down, it's extremely easy to just recover the measurements. In the previous architecture, which we had, was much more server-based, so we had to have backups and things like that. Now, all of that is, of course, automatically because you have it in the cloud, so you have a lot of the same kind of computers that are using exactly the same kind of measurement, so you can easily get it back. So to wrap up, that's what we do together with my colleagues. This autonomous measurement systems that change themselves, that change the way the companies work with measurement. Instead of having dedicated large teams to maintain measurements, we could achieve that with very, very small teams. And I'm not fan of size of the team, but that size of the team, of course, determines the cost of the measurement program. And in every company, the measurement program is not really something that you sell, right? I mean, Ericsson doesn't sell measurement systems, they sell telecom nodes. Volvo doesn't sell measurement systems, they sell cars, right? So they would like to have this same information with as little cost as possible. And that's exactly what we are doing, so maximizing the benefit with the minimum cost on it. So with that, thanks a lot. If you have any questions or any feedback, I'll be super happy to hear that. Thanks.
So one question is, typically if there are two companies, A and B, you learn something from company A and you want to use it on company B. Is company A okay with you taking learnings and applying it to company B?
Most often, yes. And in Software Center, that's never a problem.
Okay. So there are, part of the goal is also to build transferable models.
Yes.
Because that surprises me, because so let's say Volvo has improved their way of measuring, and somehow now reliability of their production has gone up. Why would they want to let this information go and be useful for the competitors, right? Because if they can make better, safer, and reliable cars, that's their IP.
Yeah, that is. But in the Software Center, the whole thing is built on the idea of that there are no competitors inside. And if you want to join a Software Center, all the companies have the right to veto. So, for example, if you have a Volvo in Software Center and then BMW would come over and say, I want to be part of that, Volvo could easily say, sorry, they're competitors, we veto that. So they cannot join. So all the companies that are in that collaboration are not competitors. Meaning that,
They work in different domains.
They work in different domains.
So from this example, A and B are not competitors. That is why they are willing to share the data.
Exactly. And of course, they don't share all of the data completely open, for example, right? So Ericsson doesn't give source code to Volvo and vice versa, right? They could meet on a workshop and show each other their code, but they're not giving that to them, right?
So how often do you see that models need tweaking? Suppose you build like a estimated defects model in Volvo, and you want to apply it in Ericsson. Does it apply off the box, or is there a fair amount of manual tuning that goes on? Like, in a sense, is the methodology the same, or is the model itself just the same? You just take the same coefficients and plug it in?
No, it's mostly the methodology that is the same. All of the companies have, even though they have maybe in some cases very similar setup of tools, they do things differently. So for example, just the sheer number of test cases that they have could be so different that the coefficient would not make sense. So based on that, but the methodology is the same. And of course, if you look at how much effort is spent on coming up to the model, of course, the coming up with the methodology first and trying out different models is what it takes time, right? And then if you know exactly what kind of steps you can do, it's much easier to replicate. It takes maybe 10% of the time, of the original time, so to say.
So
yes?
Every model is getting retrained every time you want to transfer the technology to a new company. For example, writing better code, the example you gave earlier. I can imagine writing code for a telecommunication company can be different than writing code for an automobile company. So then you have to manually or ask the company to be fully engaged again from the beginning and retrain the models.
Yeah, that's true. So if you look at this particular example of that, what we are so happy about is that it takes only 5 trials, so to say, so 5 learning cycles to get to pretty decent accuracy of the model, right? Because every company, and even within the same company, different products have different coding guidelines. Some products are written in C, some products are written in C++, and they have completely different rules. So what we are focusing on is to minimize this. So ideally, we would have just one run. Show me the code, and then I teach the model, and then I run it. But that's maybe utopic. We cannot do that. So after 5, we need to have at least today 5 runs, right, of doing that. And the whole idea that we are working on is as I mentioned, to have an ensemble learning, so that over time the rules will change, and then the model will also change, so to say. So right now we're trying to find out the breakpoint when the model should actually automatically adjust. When is the model not good enough anymore? So that the model could think about it or come up with that idea by itself. But the retraining is really important, because the rules are extremely different. And the code, how they applied and how they understood, they also very different.
And the metrics should be different too.
Now the metrics inside here, they are identical for all the companies, right? They are the set of features that we use in the model, they are exactly the same. But how you write the code, for example, how do you use capital letters or underscores will differ from company to company, from product to product. And the data types that you use also differ. So instead of coding that hard into the machine learning, we try to extract that. So we use things like bag of words to understand which language you basically use, right? What is a variable, what is a type, what is a name, what is a function. And if you look at it, if you just analyze the code, of course the keywords will pop up much more frequently than any other words, because keywords are the same, but names of variables change. So we learn, using those kind of techniques.
So you mean you dynamically identify the language
Yes.
and then apply the rules for
Exactly.
specific language?
Yes. And in some cases you can even, depends of course on the rules, but in some cases you use rules that you trained on Java code on a C++ code, because they are not that much different. In some cases, of course. Yeah?
So these checks for code, they are only trying to find, let's say, unintended, bad code, or by mistake somebody, changed the variable. How about, how would you go about trying to detect, let's say, malicious, fault in the code, right? So let's say in the case of a Volvo with the diesel cars, they were updating the variables so that it reports lower emission than actually it does. Now this was maliciously put in, right? So the software versus looking for code quality is not going to catch that. How will you catch that kind of problem?
That I don't really know, because we didn't work with that. But I guess if you have examples of a code that that does this thing, that could be applicable as well. But we have not done with those kind of.
Because if you have seen that, okay, the values for these variables always were within the range of 0 to, let's say, 50, and suddenly there's a new update to the code which makes this value 5,000. Will your system flag that right now, saying that?
Right now, no.
No?
If that's not part of the coding guideline, then it will never flag that.
How many people works on this
On this project, it's only 2 people working actively, and then we have
the whole measurement system.
We are, I think, 15, 20 people in the team, both in academia and industry. And in academia, we focus mostly on the development of the meat of that, so the algorithms. And our colleagues from industry, they usually work on applying that. So they would take that and apply that and see if that works for them or not, give us feedback and help us train the models.
You define like a measure set, the models, and then you just release it, and the development team implement it, collect all the data.
Yeah. Yes.
In the previous part of the talk, you talked about robustness of the measurements, trying to figure out which measurement should be more indicative of whatever you want to flag. What models do you use for that? Because I can imagine those being thousands of measurements that might be correlated, not correlated, and blah, blah, blah. What kind of models do you use to figure out these connections between the measurements, if there are any?
We use extremely simple models. So we start with a PCA and look which variables are collinearly correlated. And then we provide that feedback to the stakeholders, saying, look, those kind of variables, they're always in the same component, for example. And then they would say, yeah, but this metric, for example, should only be identified when it's not correlated with something else. So we don't want to see both of them in the measurement system. We want to see, for example, a delta or a deviation between one or the other, or only the weeks when they deviate somehow. But the statistical methods are not that complicated that we use.
And do you do a separate analysis of which metrics or which measurements affect which metrics? For example, if I see some measurements that are kind of dependent for this metric, they might not be dependent on another different metric. Do you do any analysis on that?
Not in that way, no. Because, we tried that, but it didn't really work out. Because the models were basically too complex. So we used graph theory to draw a graph of which metrics are dependent on what. But the models were too complex, and we couldn't really get any meaningful results.
Yeah. Okay.
So we use much simpler, PCA and just statistics, and then flag things, how they pop up.
Because your model is only as good as your interpretation of it. So if you cannot interpret those complex graphs, then you have to rely on something like that.
Exactly. That's why we, for example, also in this don't really go to deep learning or neural networks, but we prefer models like decision trees or basically decision trees, which can provide their own interpretation why they classify a specific line as a deviation and why not, so that we could use this either as a input to training if it's a false positive, or as a understanding that we are missing a feature in our model, so that we need to add something so that this line does not get recognized as a false positive. And with neural network, that's really difficult. The thing is also that for neural networks and a more complex model, you need to have really, really huge data sets, right? And you cannot really expect an architect to sit down and tag, 7 million lines of code, which lines have violations or not. So 300 and 600 lines of code is probably max what you can ask someone to help you with tagging. So you need to have a model that you can trace back and to understand that if you, for example, the model gives you a false positive, why is this a false positive? How should I provide a counter example to teach the model in a better way? And you cannot do that with a black box, with models that are black box. Hope that helps.
there are no other questions, let's start. Thanks for
Okay, thank you very much. Thanks.